So this unit, like the last one, is an important concept that's going to come up over and over again in OCHEM. And so it's very important that you take the time to really master this concept of resonance because it's going to show up. And we use resonance to explain the activity of a lot of chemical reactions or why things act the way they do. And so it's going to be very important. Now, why do we even have to go through resonance? It's something that's covered in general chemistry, and maybe you have a little bit of a handle on it. But how does resonance apply to organic chemistry? Well, let's just take a simple line angle formula. So let's look at this um, unsaturated hydrocarbon here. So we have a carbon-carbon double bond. And if I were to ask you, where are the pi electrons? Well, this line angle formula correctly identifies that the pi electrons are here in this double bond between this carbon and this carbon. And that's perfectly true. The pi electrons exist there and they are not delocalized anywhere else. But let's look at another example. Okay, so what I have here is a type of cation called a carbocation. So that carbon is positively charged. It is missing a pair of valence electrons around it. And just to kind of highlight, there are only two hydrogens attached to that carbon on the end. So like it lost a hydrogen somehow, that hydrogen left with its electrons. I'll dive more into carbocations later, but I'm just using this as an example. And I were to ask the same question, where are the pi electrons? Now, if we go strictly off of the line angle formula, we would say, well, those pi electrons should be between this carbon and this carbon. And this is a kind of case where the line angle formula actually fails to correctly ascribe where those pi electrons are. It helps us in kind of notating the structure, but it doesn't really completely describe where those pi electrons are. You say, well, where else could they be if, not between those first two carbons? Well, let's look at the molecular orbitals, specifically the unhybridized p orbitals of those three carbons. So this carbon is sp2 hybridized. This one is sp2 hybridized, as well as this one, because it only has three regions of electron density around it. So each of those carbons has an unhybridized p orbital. And those three p orbitals, they're parallel, they're consecutive, they are overlapping with each other. So that means that those pi electrons that were supposed to be between the left carbon and the middle carbon, if they're overlapping, maybe those pi electrons could be over here, maybe between these two, or maybe they're shared across all three. So the first structure there doesn't really completely accurately describe this cation. We could also describe it as this. And so this is where resonance helps us kind of rectify or to kind of put together these possible locations for these electrons. So how do I describe all of these things? So let's start with this carbocation again. Now with resonance and what we call resonance structures, we use this double-headed arrow to indicate the two possible resonance structures for this compound. And you'll hear me use the term resonance structures. You might hear me use the term resonance forms. It's all kind of the same thing. Now, I want to point out a couple of important things here. This molecule is not going back and forth between these forms. It's not like those electrons are actually moving back and forth. It's not like equilibrium. Okay, don't mix up that arrow with this arrow. Okay, so don't ever show that for resonance. That's for equilibrium. Rather, this is kind of a way for us to kind of to almost diagram what we observed on the previous page. And another important aspect of this resonance is this helps us describe something known as resonance stabilization. You're going to hear me use this term a whole lot, but this is where we're spreading out pi electrons across multiple atoms. So notice in the resonance structures above here, I have the pi electrons here and here, but then they can also be spread out across that third atom as well. Think of it this way. Let's say you're moving into a new apartment and you're moving up to like the fifth floor and you got to carry up this heavy couch to get up there. Would it be easier, and I'll use the term, would it be more stable for you to do this on your own or to get a bunch of friends? So obviously it'd be a lot easier and you'd expend less energy if you had a lot of friends to help you lug that heavy couch up 5 flights of stairs. So it's the same thing with resonance stabilization. Anytime you can spread out a charge, and I know I said pi electrons here, but that could be spreading out a negative charge, a positive charge, a single electron. We'll talk about that later. Anytime you can spread it out across multiple atoms through resonance, that helps stabilize that particular chemical species. Now, this is going to introduce us to a new concept of using curved arrows to show electron movement. So we'll use these curved arrows, and there's a tail, there's a head. We'll use like a double or a regular arrow to represent moving two electrons. A few chapters down the road, we might use like a fishhook arrow to show single electron movement, but 90% of the time we're going to be using a normal arrow. And for resonance, so I'm going to highlight this here. For resonance, these electrons always, I'm sorry, these arrows always start at electrons. And for resonance, that's going to be either a lone pair or a pi bond. Okay, so somewhere down in your margin, in your notes, and I'll write this down a little bit later as well, the tail of an arrow should never start at a single bond for resonance. That's going to change when we actually start talking about chemical reactions. But resonance is not a chemical reaction. So if we go back to our carbocation here, how do I show the transition from one resonance form to the next? I'm going to use a curved arrow. Let me change colors here. And I move it towards an adjacent atom. Okay. Notice I did not do this. Let me do a wrong way here. I did not do this and move it to that atom. Okay, that's the wrong way. Because this resonance form shows that these two carbons now have the pi bond. So that's where I'm moving that towards. So two rules right now about writing proper resonance forms, or I should say using curved arrows. For resonance, again, avoid breaking single bonds. So I'm going to demonstrate a wrong thing here. So let's say we want to, or we try to do this. Okay, notice where my Arrow is starting. My arrow is starting at a single bond. Okay, very bad. I would never do a show resonance form like this. This isn't even a resonance form. This is actually technically a chemical reaction. All right, so again, I told you write this in your margin. I'll write it down now. The tail of an arrow should never start at a single bond. And again, highlight this for resonance. We will break single bonds all the time when we do chemical reactions, but resonance is not a chemical reaction. Rule number 2 is never exceed the octet rule for second row elements. That's things like, especially like carbon, nitrogen, oxygen. Okay, we're going to use those atoms like almost exclusively when it comes to resonance. Not that you won't ever see sulfur or phosphorus, but for those elements there, those second row, carbon, nitrogen, and oxygen, never have more than 8 electrons around them. I'm gonna go off to this side here for a few examples. So you would never do this. I'm never gonna take this kind of lone pair and move it there. Because the result of that puts 10 electrons around carbon. So that's very bad. Never do that. Or, if I were to use nitrogen as an example. If I move these here to form a nitrogen-oxygen double bond, that would put 10 electrons around nitrogen. Where this gets a little tricky to notice and where students kind of make the most mistakes is when we're dealing with line angle formulas. Because you have to remember that even though you don't see the hydrogens, they're assumed to be there. So by doing this, I'm going to draw out the expanded form here. I'm going to be putting 10 electrons around that middle carbon. So I'm not going to do that. You just have to be very careful when you're dealing with line angle formulas. Now, this can always, you can get around this with one, or not get around it, but recognize this with one simple rule. Don't move electrons towards sp3 hybridized atoms because they can't accommodate anymore. They have a full octet. Now, as a side note, notice here, I underlined this word and I'll highlight it. Never exceed the octet rule, meaning more than 8. It's not a violation if a second row element has less than an octet. Let me show you an example of this down here. Let's take this for example. It is okay for me to do a resonance form like this. So I'm taking those pi electrons and I'm moving them up to the oxygen. When I do that, now oxygen has 3 lone pairs. and a minus charge because it's got extra electrons. What happened to that carbon here? This one, and I'm marking with the star. Well, it lost some electrons, so it gains a plus charge. It is okay for that carbon to have only 6 valence electrons around it. All right, so let's do a few practice problems before moving on. So with these, we're just going to see whether it violates any of those two rules that we just talked about. So letter A, if we look at the movement here, we're going from these, we're going to move those pi electrons towards that nitrogen. Now, what's the hybridization of that nitrogen? That nitrogen's sp3 hybridized. It's already got 8 electrons around it. It can't accommodate any more. So this is a violation. Nitrogen has 8 electrons already. Now, how about this one? I'm going to take these pi electrons, move them up to the oxygen. Now that oxygen's okay. It's sp2 hybridized. In fact, if I draw the resonance form of that, this is what it would look like. So oxygen's still okay. It still has 8. Carbon doesn't exceed the octet rule, and it's not a violation for it to have less than an octet. So B is okay. Now with C, what's going on here? Well, I'm proposing to move these pi electrons to make a double bond there. If I do that, what do you see the potential of that? Well, that would put 10 electrons around that carbon. Remember, there's a hydrogen there that we don't see. I'll just draw it in. So way too many electrons around that carbon. This would be a violation. The carbon, and I'm talking about the carbon with the OH, already has 8 electrons. I'd be violating the octet rule by moving those electrons there. Now in this last one, I'm proposing to move the pi electrons towards that oxygen. And for the same reason as A and C, this is a violation. There would be too many electrons around oxygen. It would violate the octet rule. Now, it is possible in moving from one resonance structure to the next that you have to move more than one, move or show more than one curved arrow. So let's look at an example here. Now, if I were to start with the lone pair on the nitrogen and move them towards an adjacent atom like this, if I did nothing else, what would happen to this carbon right here? I want you to imagine if I made that new double bond there between the nitrogen and the carbon, what would that look like? I'd have too many electrons around that carbon and violate the octet rule. So I must move these as well. So I'm going to move these pi electrons to that carbon. So what does that look like? So now this carbon has extra electrons or a lone pair on it, and the nitrogen is positively charged. Now let's just kind of look at this for a little bit. I'll talk a lot about charges in the next lecture. We're going to go into formal charge, but just kind of look at this. That nitrogen gave its lone pair to make that pi bond. It no longer has that lone pair on it. That's why it becomes positively charged. And if you think back to our first unit, I discussed like how can you recognize the formal charges without having to calculate some common formal charges for atoms, especially carbon, nitrogen, and oxygen. So you might want to go back and review that because it will save you a lot of time. You don't have to always constantly be calculating formal charge. Now in the second arrow there, so this was arrow number one, arrow number two. If you look at arrow number two, those pi electrons are moving towards this carbon atom I just marked with a star. That carbon's getting extra electrons around it, an extra lone pair. If carbon has a lone pair on it, it's going to be negatively charged. Now, this concept of resonance, drawing resonance forms, is something you have to absolutely practice. It's not going to come naturally. And this is going to either be something that haunts you throughout all of organic chemistry, or it will help you immensely in describing why molecules act the way that they do, or one tool that will help describe why molecules act the way that they do.